Hi everyone, I'm Jiamin from Tsinghua University. I'm proud to have the opportunity to present our paper, Finding Bugs in Programmable Data Plane Generators. This is a joint work with my colleagues from Tsinghua University and Alibaba Group. Over the past few years, Programmable Data Plane has gained significant traction in the networking community. The packet processing logic on the devices are programmable, and thus enable flexible customization of the network. According to the intent, programmers write data plane programs in domain-specific languages, or DSL. Then, the compiler compiles the DSL programs and generates the binary. The binary will be finally loaded on the programmable devices. However, since the data plane programming is still at an early stage, programmers have to manually take care of many hardware details and DSL specifics. This makes data plane programming not easy. Recently, a growing body of research proposes data plane generators, or DP generator. The DP generators can greatly reduce manual efforts by providing high-level primitives to express intents and directly converting intents into DP programs. Thus, many researchers and industries design various DP generators for network monitoring, routing, security, and so on. With the prevalence of DP generators, we need to guarantee their correctness. Based on our study, 3 types of mistakes may happen to DP generators. The first is intent violation. The input intent and the output program is not consistent. The second is security vulnerabilities in output programs, such as out-of-bound register access. And the third is generator crash. The generator rejects some reasonable intents without any output. Using faulty DP generators may result in serious mistakes such as missing a text and undesired packet processing procedure. Therefore, we should guarantee the correctness before using a DP generator. Unfortunately, little attention has been devoted to guaranteeing the correctness of DP generators. Existing data plane verification tools focus on verifying the consistency between specifications and DP programs. However, these tools are not designed for debugging DP generators. First, since they aim to verify individual programs instead of debugging DP generators, they can hardly cover all generator faults because they cannot enumerate the numerous intents. Second, to check intent program consistency, they require massive human-written specifications, which is error-prone and time-consuming. In this paper, we propose Firebolt, a black box testing tool to find bugs in DP generators. The key idea of Firebolt is thoroughly generating intents as test cases and automatically performing program verification. Thus, Firebolt workflow includes 2 steps: intent generation and program verification. First, to thoroughly explore the intent space, Firebolt takes the grammar and semantic constraints of a DP generator as input and generates all reasonable intents. Then, Firebolt prunes the generated intent space to eliminate redundancy and produces representative intents. These intents are input into the DP generator to generate DP programs, or to find crash bugs. To automatically verify the correctness of generated programs, Firebolt provides a general and high-level specification to express every intent grammar symbol. and automatically derives the final specification of each intent. Then, Firebolt formalizes the output DP programs using these three formulas, and use the open-source Z3 solver to check whether the Z3 formulas have security vulnerabilities or whether they are consistent with the specifications. So let's look deeper into the workflow. First, let's generate all reasonable intents. Reasonable intents should be first syntactically correct. To generate syntactically correct intents, we follow a syntax-guided generation method. Each DP generator should expose the grammar for expressing intents. The grammar describes the intent space. Firebolt uses the Becker's norm form, or BNF, the most common grammar format, to describe the intent grammar. The BNF grammar contains a start symbol and many expansion rules. These expansion rules can expand individual symbols to combinations of many other symbols. Given a BNF grammar of a DP generator, generating all syntactically correct intents can be visioned as growing an intent generation graph. The root node is the start symbol. Then, we grow the graph by replacing the symbols at each node using the expansion rules. In this example, first, the program symbol is replaced by the statement symbol. The statement symbol is replaced by two symbols, name and query. Then, we can expand the query symbol using two expansion rules and generate two new nodes. We grow the graph until all leaf nodes cannot be expanded anymore. Then, we can collect the leaf nodes as output intents. Such syntax-guided intent generation can find all syntactically correct intents. However, only correct syntax may be not enough, because they may be semantically invalid. Here, we give two examples for invalid semantics. The first example is undefined variable reference. Here, variable I1 is referenced before it's defined. To avoid this case, we should require that only after we take the expansion rules for variable definition, we can then take the expansion rules for the corresponding variable reference. This case actually represents a dependency type constraint. Taking some rules is dependent on taking other rules. The second example is repeated variable definition. To avoid this case, we should recall that if we take the expansion rules for variable definition, we should not take the expansion rules for the same variable definition. This case actually represents an exclusion type constraint. Taking some rules and taking some other rules are mutually exclusive. With these semantic constraints, we can reject some expansion rules during intent generation to generate semantically valid intents. Now, we can generate all reasonable intents. However, the intent space may be extremely large or even infinite. So next, we need to reduce the intent space and generate only representative intents which are enough to find bugs. We first analyze the factors which lead to the huge intent space. The first is the wide parameter range. A symbol may have many possible expansion rules, which correspond to a large node degree. In this example, a 16-bit number has 65,536 possible values. Worse still, this symbol appears multiple times. The exponential combination can directly lead to explosion of the intent space. The second is the cyclic reference. a symbol may return to itself after expansion, which corresponds to an infinite depth of the intent generation graph. For the first one, the wide parameter range, we can keep only representative expansion rules. The representative rules include three categories. The first is the boundary rules, such as minimum and maximum values for numbers. Boundary rules usually represent some extreme cases or conditions and should be included in the test cases. The second is random rules. We also take a random rule in addition to the boundary rule. The third is previously selected rules. When the same symbol is expanded multiple times, we also include the previously selected random rules. For the cyclic symbol reference, we break the infinite symbol recurrence by limiting the recurrence time of the same symbol expansions. Such pruning is based on the combinatorial testing theory and will not lose intent representativeness. For time reasons, I won't go into details here. Now, we have generated both reasonable and representative intents as test cases. These intents are then input into the DP generator to find crash bugs or to generate DP programs. Next, we need to automatically verify the generated DP programs to further find security vulnerabilities or intent violations. The challenge here is how to automatically convert intents into specifications for verification. Because manually converting intents into verification specifications is time-consuming and not scalable. We observe that intents are generated by expanding grammar symbols. So our key idea is first writing the specifications of each symbol in the grammar, and then automatically composing symbol specifications into specifications for each intent. To uniformly express various grammar across generators, we need to design an expression format that should be general enough to specify various grammar symbols and flexible enough for composition. We propose to express symbol specifications as high-level functions. The function is general enough to specify the input, logic, and return values of individual symbols, and flexible enough for composition by combining function calls. The function consists of two segments: a declaration function that defines internal states of symbols, and an execution function that describes the processing logic. Here, we give an example for counting. The symbol count statement can be expanded as counting on an expression. If the expression returns true, the counter will +1. So the specification for count statement is like this. The declaration function defines a counter variable. The execution function does the counting by calling the execution function of the expression symbol. Similarly, the specification of expression symbol contains the declaration part and the execution part. When we have a code snippet like this, the specification can be automatically derived by composing the specifications for count statement and expression. In this way, we can derive the specification for any intent given the per symbol specifications. Next, Firebolt formalizes the output DP programs using these three formulas. These three formulas will finally be verified. Currently, Firebolt focuses on the P4 language. Here we use the popular P416 as an example to illustrate how to formalize DP programs into these three formulas. A P416 program is composed of several programmable blocks. We convert each programmable block into these three formulas. Here we present an example for formalizing a match action table residing in the control flow block. In this example, table T matches with the key K and has two candidate actions. To formalize this table, we define a Z3 free variable for each input parameter of this table. We also convert the operations of this table to a nested if-then-else statement to imitate the action executions. Then, we can combine the Z3 formulas for different tables to derive the Z3 formulas for the control flow block. With the Z3 formulas and specifications, we can then perform program verification by converting the specification into Z3 assertions on the Z3 formulas. And then we use the Z3 solver to check whether there are security vulnerabilities in the generated Z3 formulas and whether the formulas and specifications are consistent. We implement Firebolt in a Linux virtual machine. Firebolt has about 2,000 lines of code. We use Firebolt to test 3 popular open-source DP generators, including Mapper and Sonata for network telemetry, and Poise for security policy enforcement. We take 2 DP program verification tools, Aquila and P4V, for comparison. We have 2 evaluation goals. The first is the bug coverage of Firebolt. How many bugs can Firebolt find? And the second is the scalability of Firebolt, including how long does it take for Firebolt to find bugs, and how many human efforts does Firebolt take? First, for the bug coverage. Firebolt finds bugs in all 3 generators by generating thousands of test cases, including 5 security vulnerabilities, 13 intent violations, and 1 crash bug. We also present the bug details in our paper. To evaluate the debugging scalability of Firebolt, we count the lines of input human written code and the running time for intent generation and program verification. For the running time, we can see that both intent generation and program verification in all scenarios can be done within 25 minutes. For the human written code, Firebolt requires tens of lines of code for intent grammar, tens of lines for semantic constraints, and hundreds of lines for per-symbol specifications. We can see that the per-symbol specifications occupy the majority of human written code. However, Firebolt requires writing the specifications only once, and then the specifications for all intents can be automatically derived. If we use existing tools to verify the generated programs, we need to write thousands of specifications for the generated intents. Thus, Firebolt can save massive manual efforts by writing specifications only once. Let me conclude. We propose Firebolt, the first tool to debug DB generators. Firebolt thoroughly explores the intent space to generate syntactically correct, thematically valid, and representative intents as test cases, and then automatically verify DP programs by formalizing programs and producing specifications to find bugs. Evaluation on 3 open-source DP generators show that Firebolt can achieve both high bug coverage and high scalability. Thank you for your listening, and I'm happy to take questions.